Last time we discussed the determination of acceleration due to gravity using another compound pendulum called bar pendulum. That is bar pendulum, right? So in that bar pendulum, we derived this formula. T is 2 pi under root of k square plus d square by GD, or you can write instead of BL k square plus L square over GL. So this formula we utilized in the last experiment. 2 is constant, pi is constant. We said if there is a compound pendulum of any shape, for example, there is some compound pendulum of some arbitrary shape, you pivot it at some point, right? When you pivot it, there is some point called center of gravity. If m is the mass of this compound pendulum, then what do you do? L is the distance from the pivot to the center of gravity. What is K? K is radius of gyration about which axis? Radius of gyration about an axis passing through center of gravity, which is also center of mass. Because in this room or near the surface of Earth, the variation of acceleration due to gravity, variation of the gravitational field of Earth across the given compound pendulum is negligible. So center of gravity and center of mass coincide. So this is the formula. A is radius of gyration about an axis passing through center of gravity. L is distance of the pivot from the center of gravity. G is acceleration due to gravity. And this formula is valid only for small amplitudes of vibration, because we made that approximation. To make things work, we used the approximation for small amplitudes because we made this pendulum simple harmonic oscillation by taking small amplitudes. Now, in the last experiment, we found acceleration due to gravity. Basis of the formula was this. Then what we did, we had a bar pendulum, it is a compound pendulum. This formula is valid for any compound pendulum. Now, we use the compound pendulum in the shape of the bar, which is bar pendulum. Then what we did, we plotted a graph between what? Between the time of oscillation and distance of the knife edges. Knife edges are basically what? They are pivots. We said in this bar there are 9 holes to the right of center of gravity and 9 holes to the left of center of gravity. So if this is center of gravity, the middle hole is center of gravity, and on this side we labeled one side as side A, then second side as side B. Then what we did, we plotted the time of oscillation about various pivots, that is about various holes, versus the distance of that pivot or hole from the center of gravity on both sides of center of gravity. And when we did that, we got this graph. Then what we did, we found from the graph the center of oscillation and center of suspension, right? And used that formula for acceleration due to gravity. First we found L1 plus L2. This formula T is 2 pi under root L1 plus L2 by G. L1 was what? L1 was the distance of the center of suspension from the center of gravity, L2 was the distance of center of oscillation from the center of gravity, and we put the restriction that for center of oscillation and center of suspension, the time period of the oscillation is equal. So we draw a horizontal line, then we set this point, and these 4 points have same time period of oscillation. Then we argued that if this point is center of suspension, it is at this distance, then its corresponding center of oscillation must be this point, not this one. So, if this is A is the center of suspension, then center of oscillation is this point. Because center of oscillation and center of suspension are not equidistant from the center of gravity. So if you take this point as center of suspension, then this point is center of oscillation. If you take this as center of suspension, then this point is center of oscillation. Then we found from the graph these two distances L1 and L2. Their sum was the effective length of the equivalent simple pendulum. Then we utilized that formula T is 2 pi under root L by G for simple pendulum. Instead of L, we put L1 plus L2. Once we found from the graph acceleration to the gravity, after that what we did, we used this formula K is square root of L1 plus L1 L2. We found the radius of dilation about an axis passing through center of mass or center of gravity. Then another point was to find the I, moment of inertia about an axis passing through the center of gravity or center of mass axis. So what we did, we used this formula and K square. We weighed the bar pendulum, which was about 1.52 kg. Then substitute the value of mass and K in this formula and solve for I. So we solved for G, K and I. So that was our previous experiment. Now our new experiment is to find the value of acceleration due to gravity at a place that is this lab using K-Taylor's pendulum. Now K-Taylor's pendulum is also a compound pendulum, but it is different. This is K-Taylor's pendulum. So you can see it is a compound pendulum. Now what are its parts? It has 2 knife edges. This is one knife edge, this is another knife edge. And these knife edges are adjustable. There are no holes like bar pendulum. It is one knife edge, it is adjustable, you can move it. There is a screw attached with it. It is another knife edge. So it's one part, and you can see this pendulum is in the form of a rod. It is pointed on both sides, and it has same mass distribution throughout, right? Then there are 3 other weights in it. One is this, it is also made. This weight is heavy, you can take it out of it also. This weight is heavy, right? It is made of metal, copper or brass. Then there is another weight, that is this weight. If you see, this weight has same shape as this weight. This is having certain dimensions, certain length, certain thickness, certain shape. Same is the case with this. Then what is the difference? Difference is this weight is wooden, so it's light. This weight is wooden. Why so? I will explain. This weight is wooden, that means it is light, this is heavy, right? And there is another weight at the center, which is also movable. This one. This is compound pendulum. This K-Taylor's pendulum is also a compound pendulum. So it is named after its inventor, Henry K-Taylor. Now what he has done in this? See, in the bar pendulum which we used, first we have to find the center of gravity. The center of gravity is essential in that experiment. You have to first locate the center of gravity. Only then you can do this procedure. है ना? Because you have to find the distance from the center of gravity to center of oscillation and center of suspension. Only then you can find the acceleration due to gravity using this procedure. That means in that particular experiment, when you are using that graph idea, first you have to specify the center of gravity of the compound pendulum. Now, in case of this bar pendulum, it is easy because it has a regular shape, its mass distribution is uniform, it is geometric center, the center of gravity. Now, Henry Cater invented this pendulum. Idea was, without locating the center of gravity, how to find the acceleration due to gravity using a compound pendulum. So, we don't need to locate center of gravity of the compound pendulum in this particular situation of Cater's pendulum to find the acceleration due to gravity. That is its plus point. Okay? Anybody can ask why this pendulum if you have already another bar pendulum, another compound pendulum. What is the plus point of it? Plus point is you need to find the center of gravity in order to find the acceleration due to gravity in case of Cater's pendulum. See what we do in this. First I will explain. Now you know first, if there is uniform mass distribution, then the geometric center becomes center of mass and center of gravity. So if I take these all weights away from it, I remove this weight, I remove this weight, I remove this weight, then I take only two knife edges and this bar. Right? These knife edges have also some weight. If I remove these knife edges as well, I take only the central rod. It is uniformly mass distribution. It has uniform mass distribution. So its geometric center will be center of mass and center of gravity. Now when I add these masses to it, this weight, this weight, this weight, depending on the location of these attached masses, center of mass will move. By moving this mass, I am changing the location of center of gravity or center of mass of the whole arrangement. Why so? Because when you define center of mass or center of gravity, if you change the mass distribution of a body, you can shift its center of gravity or center of mass. And center of gravity and center of mass will be closer to larger mass. Will be closer to. That means if I symmetrically locate these adjustable weights, for example, I place this weight, for example, 3 cm from the tip on this side. Then I place this weight at the same location, 3 cm from the tip, right? That is, I have located this one and this one symmetrically. Then I put this center weight at the center, geometric center, right? Then I place these knife edges also symmetrically. For example, on this side, I put it for example 3 cm from this, and this knife edge 3 cm from this. Then it will become, you have to measure these things. I am first explaining things. So if you place all these weights symmetrically, that means this weight, the location of this weight with respect to this tip, the location of this weight with respect to this tip, or you can take some other reference, location of this knife edge from this weight, location of this knife edge from this weight, location of this center weight from the tips, if all is symmetric, what will be center of gravity? It will be towards lower knife edge. Why so? Because this clever design that because this weight is heavier still than this, there is more weight towards this side. Therefore, we know for sure it will be between these knife edges, but it will be closer to lower knife edges. other weights, this weight, then we hang it. We know for sure that the center of gravity will be between the knife edges, but it will be closer to one of the knife edges, which is on the side of heavier weight. Right? Then you hang it. And I will explain how that works. Then you hang it from one knife edge. Let it oscillate. Right? Keep it something small because that is the condition. Then time its oscillation. Find its oscillating time. You count for 20 oscillations or 10 oscillations or 30 oscillations. Then find time period of one oscillation. Right? Then you repeat the process for this one. When you do it for the second knife edge, you find, you can adjust this. When you find this time period of oscillation, when you are hanging it from second knife edge, in that symmetric situation, time of oscillation for second side will be different. It will be, then what do? You move the knife edge. You can move this knife edge or this knife edge. That's your choice. For example, you decide that this knife edge I will not. You move upper knife edge. You can go up, you can go down. Repeat the experiment. Repeat the observation for time of oscillation. Until the time periods of oscillation from both knife edges are equal. Until the time of oscillation for both knife edges are equal. For example, for this, if it was 3 seconds, I am getting 2 seconds on this side. I move this knife edge. So there are two possibilities. You can bring it closer, that's your option. You will check it. If, for example, at this location I am getting 4 seconds. This observation was 3 seconds. And I move it slightly up. If it is increasing, if it is becoming 5 seconds, that means I have to go down. You adjust this knife edge until you get the time period of oscillation same for both knife edges. Now at that equal time, what happens? We can use a formula. Let me give that formula. Now I have this Kater's pendulum. This is my Kater's pendulum. Right? Now I place this one weight here, which has this adjustable screw. This is another adjustable screw. Now at the center there is another weight. Right? I place them symmetrically. So this is 3 centimeters. If this is 3, this is also 3 centimeters. If this is, for example, 12 centimeters, it is also 12 centimeters. Then there is one knife edge on this side. This one knife edge. This is also to be first symmetrically placed. Then during the observation you can change one or both. That's your option. And I have another knife edge. Right? I call it K1. I will miss that here. I will write knife edge simply. This knife edge is another knife. Right? Now I know there is some point in between. If it is heavier weight, then it will be closer to this point. For example, be center of gravity or center of mass. So let the distance from this knife edge be LE from the center of gravity of one knife edge, and distance of center of gravity from the second knife edge be LB. Right? Now I will move to that formula. Now if I oscillate this arrangement, this overall Kater's pendulum from this knife edge, I call it knife edge A. This is my knife edge B. What will be time for oscillation formula? TA. 2 pi distance of the knife edge in that formula, pivot is knife edge from the center of gravity. Got it? GLA. You can write it this way also. You can write it 2 pi k square plus LA square by GLA raised by half. That's one and the same thing. Now, if I oscillate it from another knife edge, what is the formula for time period for small amplitudes? It will be 2 pi k square plus LB square over G LB raised per half square. Right? So this is the formula. Now what I said we move the knife edges. We move the knife edges. You can move this knife edge or this or both. That is your option. That means you have to adjust LA or LB or both. So you make adjustment until TA is equal to TB is equal to common time period. I call that T. So you make adjustment in LA or LB or both. That means you can move one knife edge or another knife edge or both. That's up to you. Until the time period of oscillation about both the knife edges for the KTO's pendulum is same and equal to T. So equate now these formula. What you will get when you equate TA and TB, 2 pi will go. You get this K square plus LA square over GLA raised per half is equal K square plus LB square by GLB raised per half. Right? Then what do you do from this formula? You solve for K square. You can square it with yourself. When you solve for K square, it will turn out to be LAM. From this formula, you will get K square equal the product of LA and LB. Then you put for K square in this formula. Time period formula is T is now T and TB are both equal. You can put in one of the formulas because they are same. That's my T now, which is 2 pi. Here it was K square. Instead of K square, what I write now? For this specific situation where time periods are equal, I write LA, LB, then there is plus LA square divided by GLA, this is half. 2 pi LALB plus LA square over GLA is half. Then you solve it. When you solve it for G, you will get this 4 pi square by T square times LA plus L. 4 pi square by T square times LA plus L. This is the working formula in this experiment. Very simple. What is LALB? Sum. It is distance between the knife edges for equal time period. For equal time period. This is your LALB. You got this experiment. Now what do you have to do? You have to simply first symmetrically distribute this mass, this mass, this mass, and knife edges. Then suspend the pendulum from one knife edge, time its oscillating time, find its time of oscillation for 20 oscillations, then find for one oscillation. You can do 2-3 measurements, then take the mean for time of oscillation. Right? You can use telescope. You can focus telescope at the tip, right? And time the oscillation in order to take the precise measurement. Then you do for second knife edge. Then you adjust one of the knife edges. It is easy to adjust one of the knife edges. So through small distances you move it in order to find the precise value. Find the time of oscillation, adjust knife edge, get the same time of oscillation, then find the distance between the knife of edge at that particular situation. That's the LALB sum. Put the value, put the time of oscillation, same time of oscillation for both knife edges, get the expression to the value. Now for one arrangement you get one value. How you can get 2, 3 values? For example, if I put this mass 3 centimeter from this tip and this 3 centimeter from this, then adjust things symmetrically. In second observation, I will move this as well. Make another arrangement of the masses, symmetrical arrangement, and repeat the procedure, get another value. You do two observations. For 2 mass distributions of these weights, right? Find first G1, then G2, then find the mean of G, then find its percentage error of the G. This is the working of the system. I stop here. In the next class, you will perform this experiment. Now you know it's working. In the next class, you will perform, get the observation, get the value of G. Right? That will be part 2 of